In medicine, it's very important to be able to study and analyze the function of the kidney. And one important quantity, one important measurement that doctors use to actually study the function of our kidney is known as the renal clearance. So this will be the topic of this lecture. Now, what exactly is renal clearance? Well, renal clearance of a given substance basically tells us how much volume of blood plasma is completely cleared of that substance over some time period by our kidneys. And the units of renal clearance are milliliters, the volume per minute, our time. So, let's begin by taking a look at the simplified diagram of our nephron, the basic functional unit of our kidney. So we have the afferent arteriole that brings our blood vessel, that brings the blood plasma into the network of capillaries found inside the Bowman's capsule known as the glomerulus. Now, within this network of capillaries, we have filtration taking place. Some portion of the blood plasma that enters the glomerulus is filtered through a filtration membrane and into the Bowman's capillary, or the Bowman's space of the Bowman's capsule, and then enters our tubular section of the nephron, which includes the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, as well as the collecting duct. Now, within the tubular section, we also have reabsorption and secretion taking place. Now, the rest of that blood plasma that is not filtered travels into the efferent arteriole that then enters our peritubular capillaries, and these are the capillaries where we have reabsorption and secretion taking place between the blood capillaries and our tubules of the nephron. Now, let's begin by discussing the rate at which blood actually flows into the nephron for normal kidneys. Now, the normal kidneys pass about 625 milliliters of blood plasma through the afferent arteriole and into the glomerulus every single minute, and this is known as the renal plasma flow, where flow is simply the movement of our fluid. The plasma is the blood plasma that moves across our blood vessels, and renal refers to our kidneys. So 625 milliliters of blood plasma passes through the afferent arteriole every single minute. Now, in our discussion on the renal corpuscle, the glomerulus, and our Bowman's capsule, we said that about 20% of that blood plasma that enters our glomerulus is actually filtered into the Bowman's space of the Bowman's capsule and then enters the tubules of our nephron. And because 20% of 625 is 125, that means 125 milliliters of blood plasma filters through the glomerulus every single minute. Now, because we have 625 going in and 125 comes out of this side, then that means this minus this, or 500 milliliters of blood volume, actually travels through the efferent arteriole and into the peritubular capillaries every single minute. Now, the filtration rate of 125 milliliters per minute is also known as the glomerular filtration rate. So this is the normal filtration rate of the glomerulus, and this is the normal value for the renal plasma flow. Now, recall, as we mentioned earlier, within our tubular section of the nephron, we have reabsorption and secretion taking place between our peritubular capillaries. So certain substances that are actually filtered across and into the Bowman's capsule are reabsorbed back by that body, and this includes things like amino acids and glucose, sodium chloride, as well as as many other things. Now, we can also have secretion taking place. Certain substances that end up traveling into the efferent arteriole and then into the peritubular capillaries can actually be secreted back into our filtrate and eventually ends up in our urine that is released by our body. So we see that there are actually only two ways by which a given substance can actually end up being in the filtrate and eventually ends up in our urine and is released by our body. And these two methods are as follows. Number one, that substance can be filtered through our glomerulus and then not reabsorbed by our tubules. And what that means is that substance, because it is filtered and not reabsorbed, it will end up being in the urine that is released by the body. Now, the second method is the following. It is not filtered through our glomerulus, but as it travels through the efferent arteriole and eventually ends up in the peritubular capillaries, it can be secreted by those capillaries into the tubules, and then it ends up in our urine. So these are the only two ways by which some given substance can end up in the filtrate and ultimately released in our urine. Now, as I mentioned earlier, different substances have different values for the renal clearance. So let's begin by supposing we have some hypothetical substance. Let's call this substance X, and let's discuss how it can actually move within our nephron and what can happen to it within our nephron. And let's study what the renal clearance value is of this substance. So I've outlined 4 different cases, but you should note that there are more cases than this. These are probably the 4 most common cases that you should be familiar with. Case number 1. So we basically have freely filtered through the glomerulus. And what this basically means is whatever this substance is, when it enters this blood plasma, when it enters the glomerulus, it can easily pass across our glomerulus. And that means the concentration of this substance in the Bowman's capsule will be exactly the same as the concentration of the substance inside our blood plasma found in our glomerulus. Now, not absorbed means when that substance is within our tubule of the nephron, it is not reabsorbed back into our peritubular capillaries. And not secreted means if any of this substance is found in the efferent arteriole, it is not actually secreted by the peritubular capillaries back into our filtrate. So case number 1, freely filtered, not absorbed, not secreted. So for a substance X that is freely filtered via the glomerulus, but it is neither reabsorbed nor secreted, what exactly will be our renal clearance? Well, let's take a look at the following diagram. So we basically have 625 milliliters of blood volume enters this glomerulus every single minute. And every single minute, 125 milliliters per minute is actually cleared. Now, because this substance is assumed to be freely filtered, that means 125 milliliters per minute is actually filtered. So that means as it passes across the tubular section of the nephron, because none of it is actually reabsorbed and none of it is secreted by these peritubular capillaries back into our tubule, the filtrate, that means the renal clearance is simply equal to our glomerular filtration rate of 125 milliliters per minute. So this quantity of blood plasma that enters this tubular section of the capillary is completely cleared of that substance. Now, what's an example of such a substance? Well, one example that is not naturally found in our body, but our doctors use to study the glomerular filtration rate is known as inulin. So inulin is this polysaccharide that we can basically ingest into our body, and which is basically follows this pathway as described. So it is completely filtered by our glomerulus. It can basically travel across freely, but it is not reabsorbed, nor is it actually secreted. So the glomerular filtration rate, or GFR, is equal to the filtration rate of this substance, our inulin. So our doctors basically can study the glomerular filtration rate of our kidneys by giving the patient this substance and then studying what our renal clearance is of our inulin. Now, let's move on to case number 2. In case number 2, we also have the substance freely filtered, but now it is fully reabsorbed and it is not secreted. So let's take a look at what that actually looks like. So we have 625 milliliters per minute coming into our capillaries, the glomerulus, and because it is freely filtered, it passes freely across, so that means 125 milliliters per minute flows into the Bowman's capsule and into the tubular section of our nephron. Now, because it is fully reabsorbed, that means all that substance found within the 125 milliliters per minute is completely reabsorbed back into the peritubular capillaries that are found in close proximity to the tubular section of the nephron. And that means 125 milliliters per minute will basically be filtered back into our body. Now, what does that tell us about the renal clearance of such a substance? Well, if we take this and subtract this, we simply get 0, and that means the renal clearance of this substance is 0 milliliters per minute, or none of that substance is actually removed from the blood plasma. Now, in what cases does this actually take place? What are some examples? Well, some examples include glucose and amino acids. So remember, glucose and amino acids are tiny enough to actually be filtered across our glomerulus, but these are important nutrients that are needed by the body. And that means we don't actually want to lose these nutrients, and that's exactly why these nutrients are reabsorbed back by our body. Now, let's move on to case number 3. So in case number 3, we have freely filtered, we have not absorbed, but we have fully secreted. So let's take a look at what happens. We have freely filtered, so that means out of the 625 milliliters per minute that comes in, 125 milliliters per minute is basically filtered through our membrane into the tubular section of the nephron. Now, when the filtrate is traveling through our nephron, it is fully secreted. That substance that ends up in the peritubular capillaries is fully secreted into our filtrate found traveling along our tubular section of that nephron. So what does that tell us about our renal clearance? Well, because none of it is actually reabsorbed, we have 125 plus 500, and that gives us 625 milliliters of blood volume. Every single minute is cleared, and that means none of that substance will actually remain in our blood plasma. And one example of such a substance is PAH, which stands for the para-aminohippuric acid. So this is a substance that is essentially completely cleared by our body. Actually, a small percentage of it is left over in the blood plasma, but for all approximation purposes, we can assume that all of it is actually cleared. Now, what about case number 4? So here we have freely filtered, only slightly reabsorbed, and none of it is actually secreted. So let's take a look at the following example. So we have 625 milliliters per minute is the renal plasma flow that enters our glomerulus every single minute, and because it's freely filtered, 125 milliliters is cleared every single minute. But when the filtrate is traveling within our tubular section of our nephron, a small amount, some amount is actually reabsorbed back into our body. Now, in this case, it was fully reabsorbed, so we have a renal clearance of 0. But in this case, only a slight amount was reabsorbed, and that means whatever the renal clearance is, it will be slightly less than 125 milliliters per minute, but it will be greater than 0 milliliters per minute. Now, one example of such a substance is urea. Urea is small enough to actually filter easily through our glomerulus, but a small percentage of it is actually reabsorbed. In fact, 60 milliliters per minute is reabsorbed. And that means 125 milliliters per minute minus 60 milliliters per minute gives us about 65 milliliters per minute. So this is the renal clearance of urea. This is how much volume of blood plasma is cleared of urea every single minute by the nephron of our kidney. Now, there are other cases that exist. For example, we can have a case where we have freely filtered, not absorbed, but slightly secreted. And in this case, we'll have a renal clearance value somewhere between 125 milliliter per minute and 625 milliliters per minute.